Okay, it's 3 o'clock. It's time for our last contributed talk of the afternoon. Will be by Ian Montague from Brandeis on Seiberg-Witten Floer K-theory and cyclic group actions on spin-4 manifolds with boundary.
All right, thanks for the introduction, Greg. Today I'm going to be talking about 10/8 types inequalities for spin-4 manifolds with boundary emitting cyclic group actions. All right, so recall the 11/8 conjecture posited by Matsumoto in 1982, which says that if W is a closed indefinite smooth spin-4 manifold, then B2 of W is greater than or equal to 11/8 times the signature. And this is still an open conjecture, but we have the following theorem, which almost gets there, aptly called the 10/8 theorem by Furuta in 2001, shows that B2 is greater than or equal to 10/8 times the signature plus 2. All right, and so without loss of generality, for the rest of the talk, we're going to assume that the signature of our manifold is non-positive by reversing orientation if necessary. And let's let P be equal to minus the signature over 8 and Q be equal to B2 plus of W. All right, then we can rewrite the 11/8 conjecture as Q is greater than or equal to 3/2 P and 10/8 conjecture as Q is greater than or equal to P plus 1. All right, so that's for closed manifolds. What about spin-4 manifolds with boundary? All right, and in 2014, Manolescu proved the following relative 10/8 type inequality, shows that if W is an indefinite spin-4 manifold with boundary a rational homology 3-sphere, then Q is greater than or equal to P plus 1 minus a certain correction term called the kappa invariant of Y. All right, so in general, kappa of Y is a rational number. It's defined via the pin 2 equivariant K-theory of the Seiberg-Witten Floer spectrum denoted by SWF of Y, which we'll talk about later. But I just want you to note that kappa invariant of the 3-sphere is, with its unique spin structure, is 0, and so this recovers the 10/8 theorem of Furuta. All right, so question we want to ask today is whether we can do better if W emits a spin Z mod M action. Right, and so the answer is yes, otherwise I wouldn't be giving a talk today. But what exactly is a spin action? All right, so we have to be careful about our category of group actions on the manifolds we care about. So for the following, let M be a spin 3 or 4 manifold, and S denotes the spin structure, the chosen spin structure on M. And let's let tau be a diffeomorphism of order little m on big M. All right, then we define a spin lift tau hat of tau by the following commutative diagram. So basically, we have tau acting on the manifold M below. For free, we get an bundle automorphism of the associated SO and frame bundle, denoted by d tau, which just transports frames. And then the by definition, right, the spin structure is a 2-to-1 cover of the frame bundle, and so tau hat is just a lift that 2-to-1 covers d tau. All right, and so spin lifts come in 2 flavors, which is kind of peculiar. So we say that tau hat is of even type if it's of order M, and of odd type it's of order 2M. The terminology seems a little backwards, but there's some deep reason for it, which we won't go into. Just go into some examples. All right, the types of spin lifts that you're able to get depend on the topology of your action. All right, so for example, consider the involution on the forward ball sitting inside of 2-dimensional complex space. All right, let's let tau be the involution, which spends zw to minus z minus w, then it turns out that any spin lift of this involution is of even type. All right, and for a second example, let's let F be some surface inside of some four manifold, and consider the double branch cover of X over our surface F. And let's let tau be the covering involution. All right, so if a spin lift exists, then any spin lift of this action has to be odd, right? And this follows from a deep theorem called the Atiyah-Bott lemma for spin actions. Okay, so with that out of the way, let's state some theorems. All right, so with this framework, we have these kind of equivariant 10⁸ type theorems for closed four manifolds, due independently to Brian, Feng, and Kim. All right, so let W be a closed Z mod 2 to the R equivariant spin four manifold, tau hat of either even or odd type. Then we get that Q is greater than or equal to P plus 1 plus R. All right, so essentially, if we have a 2 to the R fold action, then we can do R better with our inequality. We can eke out just a little bit more. All right, so that star here means this is under certain technical conditions, which I will totally brush under the rug. All right, and so all right, with the following theorem for manifold boundary. So W Z mod 2 to the R equivariant spin four manifold with boundary a rational homology 3 sphere. Then we have that Q is greater than or equal to P plus 1 plus R minus Manolescu's kappa invariant of Y, again under certain technical conditions, which again we'll brush under the rug. All right, so you can see that this is like the natural like push out of like the theorem up top and Manolescu's theorem without the cyclic group action. All right, so before we get into how this is proven, be nice to see how we can apply this to certain topological questions. But before we can do that, I'm going to state a few more related theorems, which fall under this framework. All right, so for the following, let's suppose we have, in general, a Z mod M action on a four manifold W. I'm going to denote by B2 plus W sub K the dimension of the e to the 2 pi I K over mth eigenspace of Z mod M acting on H2 plus of W with complex coefficients. All right, so for example, in the case of an involution, B2 plus W splits into B2 plus W sub 0 and B2 plus W sub 1, which are the plus 1 and minus 1 eigenspaces of this action, respectively. All right, so with that being said, here are the following related results. Let's consider just involutions with spin lifts of odd type. In 2017, in the closed case, Kato proved that B2 plus W sub 1, the non-trivial part of B2 plus, is greater than or equal to minus the signature over 16. All right, so in some sense, we kind of have half of the usual 10⁸ types inequality here. All right, and just last year, Kono, Miyazawa, and Taniguchi proved that if we have W with boundary rational homology 3 sphere, then B2 plus W sub 1 is greater than or equal to minus the signature over 16 minus a new kappa invariant that they've defined called kappa of KMT, which is in general different than Manolescu's kappa. All right, so I know it's a lot of technical inequalities. All right, let's kind of put them together and see what we can get out the other end. All right, so here's just a organization of these inequalities. All right, so we have Kono, Miyazawa, Taniguchi's inequality, Manolescu's inequality, and then my inequality. In the case of odd type involutions, I can eke out one more for the inequality. All right, so put in some work and get a little bit extra out of it. And if we're lucky, so if the trivial part of B2 plus W is even, then I can get a plus 3 in there. Okay, fine. Let's see how this all shakes out. All right, so what we're going to do is see how we can apply this to genus bounds inside of four manifolds. All right, so consider the following situation. Consider any old closed four manifold and surface F inside of the punctured four manifold, such that its boundary is equal to some knot K on the boundary 3 sphere, and let A denote the homology class of F sitting inside of each of it, H lower 2 of X. And so we have the following picture over there. All right, so here's the idea. So first, what can we do in this situation? Let's define G sub X comma A of K as the minimum genus over all surfaces inside of X minus a 4 ball with boundary K and its homology class equal to A. And so note that this is a natural generalization of the usual 4 ball genus, right, where X is taken to be S4 inside the zeroth homology class. Okay, so we'd like to see how we can get bounds on this XA genus. All right, so here's the idea. If in this situation we happen to have that the homology class of F is divisible by 2, and that F over 2 is equivalent to the second Seiberg-Witten class of X modulo 2, then the double branched cover of this punctured manifold over F is spin with a distinguished spin structure that is invariant under the covering introduction, right? And so therefore, we can apply a relative 10⁸ type inequalities of this manifold with this evolution to give us bounds on the XA genus. All right, so let's see how that looks in terms of the inequalities I showed before. All right, so there's the definition of the XA genus. Up top we have the K and T inequality, and then my inequality right below it. And so what's kind of nice is that these two inequalities, they look pretty similar, but there are a few key differences. There's a lot of things going on there. I don't want you to parse every detail of the inequalities, but just look to see the similarities and the differences. And the main difference is that in front of the knot signature in the K and T inequality, there's a minus sign. In front of the knot signature, my inequality is a positive sign. All right, and so their inequality works better for negative signature knots. Mine works better for positive signature knots. All right, so they kind of complement each other nicely. All right, so that one's hard to work with. All right, kappa invariants are in general extremely hard to compute, but we can focus on a special case. All right, so let's let HL be the set of knots in S3 such that the Seiberg-Witten Floer spectrum of the double branch cover of K with its unique invariant spin structure is homotopy equivalent to a sphere for some n. All right, so the HL stands for homotopy L space. So if you'd like, it's kind of like saying that the double branch cover is an L space. And so in particular, this class of knots includes connected sums of all two-bridge knots and a list of knots that are listed there. And conjecturally, some others, not an exhaustive list. All right, so in this case, we can compute the kappa invariants explicitly, and they're basically given by the D invariants of the double branch cover coming from Heger-Floer homology. And by theorem of Lin, Ruberman, and Savliev, these are basically given by the knot signature. All right, and so our inequalities simplify nicely. All right, so again, don't look at the whole thing, but I just want you to notice the different coefficients and how they complement each other. And so, let's take a nice example, the connect sum of two CP2s. All right, let's let F be in the homology class A comma B, all right, then we get the following two inequalities. All right, so yeah. All right, so just to give you an example of how we can use these types of inequalities in practice. Okay, so all right, so that's for applications. I kind of want to go back to our theorem in its full generality as stated before. All right, so I put the theorem before. And I want to point out that this actually follows from a much more general theorem and construction. All right, so now we'll kind of get into the nitty-gritty of things, but I'm going to be a little hand wavy. Let's let pin 2 be equal to the S1 disjoint union J, S1 sitting inside of unit quaternions. All right, and we'll define the following two groups. So G eve M is just going to be the product pin 2 times Z mod N, and G odd M is going to be pin 2 times Z mod 2M, and then modded out by the diagonal Z mod 2 side. All right, so you can think of this as kind of like a twisted product of pin 2 and Z mod M. All right, so why do we care about these groups? Well, it turns out that for an equivariant rational homology 3-sphere, right, we can construct a G star M equivariant stable homotopy type SWF of Y S comma sigma hat, where G, star is either even or odd depending on the parity of that spin lift sigma hat of sigma. All right, so here's kind of like the big general outline of how our invariants are constructed. All right, so we abstractly have this equivariant spectrum. And what we're going to do is we can look at the set of S1 fixed points of the spectrum, right? And look at the inclusion map of the S1 fixed points into the full spectrum. And we're just going to whack it with G star M equivariant complex K theory. And so this gives you map going backwards. All right. And what's nice about these spectra, you can prove that the equivariant K theory of the S1 fixed points is actually just isomorphic to the representation ring of G star M, the complex representation ring. All right. And this is like a concrete thing, and in particular, it's a polynomial algebra. And so what we can do is look at the image of this map, iota star, and think of it as an ideal sitting inside of this representation. Right? And basically, what we do is like construct a numerical invariant from this ideal sitting inside the representation. All right, so with the time I have remaining, I'll hand wave around a little bit. All right, so J defined to be the image in equivariant K theory sitting inside the representation ring. All right, so there's a fact. The representation ring of these groups are generated by some variables W0 through Wn-1. In the even case, we have variables Z0 through Zn-1. And in the odd case, we have Z1 half through Zn-1 half. So you can think that in the odd case, we have odd multiples of 1/2, the Z variables. Okay, so we want to kind of simplify this a little bit. All right, so the first thing you notice is that if we multiply everything in the ring by W0, then it lands in the ideal generated by W0 through Wn-1. Right, so it kind of kills the Z variables. Right, and so this kind of collapses our ring into a smaller subring, which is a lot more palatable. It's just generated by M variables. And then what we do is define some set S, which, I don't want you to parse through the whole thing, but basically we look at M tuples sitting inside of the natural numbers, such that there exists X inside the image of this ideal, such that if we hit it with W0, then it equals this monomial in the WK variables with these particular exponents. All right, and so we're kind of extracting a semi-lattice from this this ideal. All right, so particularly we endow n to the m with the partial order. The k is less than or equal to L if and only if that's true component-wise. All right, and then we define the set of equivariant kappa invariants to be the set of minima of this subset with respect to this partial order. All right, and then just a side note, all right, technically our spectrum turns out it's a formal rational desuspension of the space by rational linear combination of representation spheres, and so we end up getting something in q to the n, but that's not important. I just want to leave you with this kind of picture going on. All right, so let's look at a particular example. Let's let y be the 2, 3, 11 rescored sphere with the involution iota sub Mont, which realizes it as the double branch cover of Montesino style. Then the set S inside of R2, just think of this like the shifted quadrant, and its unique minimum is 0, 1. And so that is our kappa invariant. Now we can look at the same three manifolds, but with a different evolution, which realizes it as the double branch cover of the 311 torus knot. And it turns out that we get two shifted quadrants. And you can see with respect to this partial order, there's kind of two minima, 0, 1, and 1, 0. And so our set of equivariant kappa invariants consists of those. All right, so these spectra see the difference between these two evolutions. All right, and then so finally have the following theorem, which I'll end on this slide. Let W be a Z mod M equivariant filling of some rational homology 3 sphere Y. All right, let Q be the vector inside of Q mod M, which is kind of Q to the M, which is this like equivariant decomposition of P2 plus as a vector. We're gonna let P be a certain vector. I'm not gonna go into it. It's kind of like an equivariant decomposition of the signature, but it's not an equivariant signature. It's a little annoying, but if you add up all its components, it's equal to minus the signature of W over 8. And then let E sub K be the KT vector. All right. Then we get the following statement. All right. So essentially, since we're working in this kind of lattice of a partial order, right, we don't get one inequality. We kind of get these two statements. Right, for all kappa sitting inside of this set of invariants, Q is not strictly less than P plus E0 minus kappa, and there exists some kappa inside of our set of equivariant kappa invariants such that Q is greater than or equal to P plus E0 minus kappa. Right, so this is nice to compare this. This is a natural generalization of Manolescu's inequality. Q is greater than or equal to P plus 1 minus the kappa invariant of Y, comma S. Right? And don't have enough time for the rest, so I'll just leave you on the slide comparing all the inequalities and end it there.
Okay, well, let's thank our speaker. Any questions? I actually have a very probably elementary question from way back on the first or second slide. So there you said that without loss of generality, we could focus entirely on manifolds whose signatures are negative or at least non-positive. Mm-hmm. Maybe this is something I should know, but why don't we lose generality doing that?
Oh, yeah. So, you know, I like the way that the those inequalities were stated, right? So I guess go all the way back to the beginning, right? They're kind of in terms of like absolute values of the signatures. And so like, basically like what you can do is like switch it to be non-positive, right? You prove your inequality, and then like, if you switch it back, then it like gives you the result that you want, if that makes sense. Yeah, no, that's a good question. Sorry, I kind of skirted around that a little bit, but yeah.
I think I see. Okay. Any other questions? No? Okay, if not, let's thank Ian again. Quiet group today. So that will be it until the principal talk at about 4 o'clock. 4 o'clock Central Time, so about 35 minutes from now. Okay, thank you to the speakers from this session.